All right, let's talk about Kepler's laws. We've talked a little bit about what happens when things go around things like stars, and it turns out that a famous astronomer, Tycho Brahe, and his assistant, Johann Kepler, came up with some laws to describe the orbits of planets around a star. Science has been watching the skies for a really, really long time. We've noticed that most of the lights in the sky seem to stay in one place relative to one another. They do rotate because the Earth rotates, but the shapes stay the same. But a few of these lights seem to wander from night to night. In Greek, the word planeta means wanderer, and that's how we distinguish those few lights in the sky that seem to move around. We call them planets. Ancients knew about a series of wanderers that were visible to the naked eye. Mercury, Venus, the Sun, the Moon, even though those aren't planets, Mars, Jupiter, and Saturn were all seen to move from night to night. There was some evidence that Uranus was also occasionally seen and determined to wander. But it turns out that Uranus is so far away from the sun that its wandering from night to night would be really hard to discern. Anyway, scientists observed these planets and tried to make rules predicting how they would move. This proved to be really, really difficult until Copernicus correctly placed the sun at the solar system center rather than the Earth. That was a big step. Then there was the astronomer Tycho Brahe, who was considered the greatest naked eye astronomer in history. Without the use of any telescopes, which hadn't been invented yet, he observed and recorded data for nearly 30 years. One of his assistants, Johann Kepler, took all this data and was able to formulate 3 laws to describe planetary motion. Kepler's first law, or K1 as I'll call it, states that the shape of planetary orbits are ellipses, with the sun at one focus. There's nothing at the other focus, just worry about the sun being at one focus. We've talked about circular motion, and it turns out that except for Pluto, and this is one of the reasons Pluto is no longer considered a planet, all the planets' orbits are so close to circular that it would be difficult to tell. So we can make the assumption that it's circular. If you remember from your geometry and your math classes, a circle is really just a special ellipse. Nonetheless, we now know that the planets do move in elliptical orbits. K2 states that a planet's orbit, it sweeps out equal areas and equals time. This is a confusing way to state that the closer a planet is to the star, the faster it moves. You should remember that K2 means that closer means faster. Remember the closest planet to the sun. It's Mercury, named after the Roman messenger god. Mercury was very fast, just like the planet. Here's a graphic of K2. Here the planet is near the sun, so it's moving faster. Here the planet is far from the sun, so it's moving slower. You need to look at the two areas, the two blue areas. Each area, if you calculate them, would be the same. So if we assume that it took 1 month to travel each distance, travel the faster distance or further distance in the faster time and a lesser distance in the slower time, the areas would be the same. That's what we mean by equal areas and equal times. I think it's better to remember that faster to the star means it moves, or closer to the star means it moves faster. Now let's go to Kepler's third law. This would be K3. Since we're concerned with modeling, we're going to graphically and mathematically model the relationship between, to Gamter, the planet's orbital distance from the sun and its orbital period to the sun. We will essentially be doing the very same math that Kepler did, about 400 or 500 years ago. Here's the planetary data. We only have 8 planets. Sorry, Pluto, we're not going to include that. And these are the data. Notice that we've listed the distance to the sun in terms of an astronomical unit. By definition, the Earth is 1 AU away from the sun. It's just a convenient way to talk about distances. So we can compare other planets' distances to the Earth's distance using AUs. So we're going to list all the planets in terms of Earth's orbits, or AUs. We also use the orbital period as a year. Again, that makes sense. We know that it takes the Earth 1 year to orbit the sun, so we can list the orbital periods of the other planets in terms of Earth years. If I graph the data, this is what it looks like. It's clearly not a line. We could do all sorts of statistical analysis like we do in LoggerPro to convince ourselves that it's not a line. So it looks like we need to do some work in linearizing the graph. We've done that before. I've given you some worksheets, I've given you some hints in how to linearize the graphs. It turns out, however, that this relationship is one of the more complicated ones. So the typical methods we've used aren't going to work here. It can't be related or linearized using the techniques we've learned. So in this case, we're going to use a different fit, that of a power fit. Using log or pro or XL, we're going to fit to the function y equals ax to the b power plus a constant. Doing so gives us the following result. Look at that data. The r squared is 1. I get almost a perfect fit. The lines go right through the data points. It's a great fit. We find that the orbital period is equal to the distance that the planet orbits to the 1.5 power. It also shows that the constant c is about 0 and a is essentially 1. If we square both sides of the equation, we get the result that t squared is equal to r cubed. This is what Kepler found. He expressed it in the following way. He said that r cubed over t squared is equal to a constant. What that constant is, we don't care. We just know that it's going to be a constant. He didn't really know why it was true. He just knew that it was true. Newton is going to be the one that showed us how that's the case. Anyway, we'll show why K2 or 3 is true in a bit. Here I want to summarize Kepler's laws. K1, the shape of planetary orbits are elliptical, with the sun at one focus. K2, the closer you are to the gravitational attractor, whatever you're orbiting, the faster you move. It's another way to say equal areas and equal times. And then K3, the ratio of the orbital distance cubed to the orbital period squared is a constant for all objects orbiting the same gravitational attractor. Oftentimes, we're going to call this constant in K3 the Kepler constant. It has a different value for each gravitational attractor. So, if we're talking about things orbiting the sun, every planet will have the same Kepler constant. But if we talked about a different star, the Kepler constant would be different. So make sure you can keep that distinction clear. Let's try an example using our solar system. We can usually find the Kepler constant for our sun using the information about Earth. We know that the distance that Earth orbits is 1 AU and that the orbital period is 1 year. So if I put everything in there, I find that the Kepler constant is 1. That makes it real easy to do calculations. So in terms of AUs and years, the Kepler constant for our sun is 1 AU cubed per year squared. We know that Jupiter has about a 12-year orbital period around the sun. We can make observations and see that. So how far from the sun does Jupiter orbit? If I put the numbers in, I get r cubed over 12 squared is equal to 1. I do a little bit of rearranging. I find that r cubed is equal to 144 years squared. And if I take the cubed root, or I cancel out the year squared, take the cubed root, I find that the orbital distance is about 5.24 AUs. That's what we'd found before. Even though Pluto is now considered a dwarf planet and not a regular planet, it does orbit the sun, so it has to obey K3. We know that Pluto is about 39.4 AUs from the sun. How long does it take Pluto to orbit the sun? Putting in the numbers again, I get 39.4 cubed over t squared must equal 1. That means t squared is equal to 61,163, or t is about 247 years. We've known about Pluto for about 100 years, so it's really only made about 40% of its orbital journey around the sun since we've discovered it. Be careful to realize that the Kepler constant only equals 1 for our solar system when the units of distance are in AUs and the units of time is years. This is unique to our star. Each star in our galaxy has its own Kepler constant, and it's almost certainly not equal to 1. Let's find our sun's Kepler constant in terms of the SI system of units. We know that 1 AU is 1.5 times 10 to the 11th meters. We know that 1 year is 31,557,600 seconds. Putting those values in, I find that the Kepler constant for our sun in terms of meters and seconds is about 3.4 times 10 to the 18th meters cubed per second squared. Which Kepler constant do you use? Well, it depends upon your problem. Look at what's given in the problem, see how the information is presented, see what units are given, and then use the appropriate Kepler constant. Let's try another system that we're familiar with, that of the moon orbiting the Earth. So in this case, the Earth is the gravitational attractor, not the sun anymore, so we don't have to use 1 for our Kepler constant. It wouldn't make sense. We should be able to find the Kepler constant for anything orbiting the Earth. As I've mentioned before, we are familiar with the moon orbiting the Earth. The orbital distance of the moon from the center of the Earth is, 3.84 times 10 to the 8th meters. That's a really big number, so I want to express that distance in terms of Earth radii. The radius of the Earth is 6.38 times 10 to the 6 meters. If I divide the two numbers, I find that the distance from the Earth to the moon is about 60.2 Earth radii. That's going to be a little bit easier number to use. How long does it take the moon to orbit the Earth? A month. We know that a lunar month is about 29.5 days, or 2,548,800 seconds. So I can calculate the Kepler constant for the Earth in terms of ER cubed over days squared. Put in the numbers, I find that that value is about 251. 251 Earth radii cubed over days squared. Very, very different from the 1 AU cubed over years squared. But again, we have a different gravitational attractor and we're using different units. We typically use units to calculate the Kepler constant that make the calculations as easy as possible. How about if I convert that into meters and seconds? Putting in the numbers, I get 8.72 times 10 to the 12th meters cubed per second squared. Notice how much smaller that value is than for the sun. That seems to indicate that the Kepler constant may have something to do with the gravitational attractor's mass. Sun seems to be much bigger than the moon, has a much bigger Kepler constant. Obviously the Earth is much smaller, so that's going to make sense. So let's now look at why K3 is true. It turns out to be simple math relating uniform circular motion and Newton's second law. Consider a planet of mass m sub p orbiting a star of mass s, or m sub s. It orbits in a circular orbit at a distance r from the star with an orbital period of t. Here's the drawing I have. You can see the acceleration vector directed towards the center. That's where the sun's located. And then the velocity vector perpendicular to it. Again, even though it's elliptical orbits, it's so close to circular orbits that the difference doesn't matter. The only force acting on the planet is gravity. And for that, we're going to use the null expression. We also know that the planet has to obey uniform circular motion. So then F is equal to m a sub c. For a sub c, I'm going to use the expression that has r and t in it. This gives the relationship. G, mass of the sun, mass of the planet over r squared is equal to the mass of the planet times quantity 4 pi squared r over t squared. Notice that the masses of the planets cancel. And then I'm going to be rearranging, and I'm left with r cubed over t squared is equal to g, mass of the sun, over 4 pi squared. Wow, look at that. The left side is K3. That's where K3 is going to come from. Look at the right side. It's a series of constants, including the mass of the star, and g we know, and then the 4 pi squared is obviously a constant. So it appears that the Kepler constant is completely determined by the mass of the planet or the gravitational attractor. In fact, if we know the Kepler constant, we can determine the mass of the gravitational attractor. For the sun, we calculated before, the Kepler constant, 3.389 times 10 to the 18th meters cubed per second squared. We can use that value to determine the mass of our sun. From that, because we know what big G is, we find that the mass of the sun is 1.99 times 10 to the 30th kilograms. It's a huge number. Arguably one of the biggest numbers humans have ever had to calculate. And it's completely determined from the physics that you now know, that of Newton's laws and uniform circular motion. So, if we know how far something is from the gravitational attractor, how long it takes to orbit, we can determine the mass of that gravitational attractor. It works for anything. It works for the Earth, it works for the planets, it works for the sun, it works for distant stars, it works for our galaxy. Believe it or not, our sun does orbit the center of the galaxy. We know how far away that is. We know how long it takes. We can calculate the mass of the supermassive black hole located at the center of our galaxy. We've known for centuries that planets like Mars and Jupiter, Saturn, and Earth have orbiting moons, so we can use K3 to determine the mass of those planets. Once we observed Uranus and Neptune, we noticed that they had moons orbiting them as well, and we can get those masses by the same method. We did not accurately know the mass of Venus till the 1960s, even though we've been observing Venus for about 400 or 500 years. Finally, in the 1960s, when the USSR and the US sent missions to Venus, they orbited the planet. Once we get the orbital distance and the orbital period of those satellites, we can determine the mass. We finally sent an orbiting spacecraft to Mercury in 2011. The Messenger spacecraft got there, and finally then we were able to determine what the mass of Mercury would be. So Kepler's laws and the use of K3 to determine these masses and to do the rocket science that we use may be one of mankind's greatest discoveries since fire. I think it's really cool. Hopefully you do too.